Good morning, sir. I am Rahul Ghosh. In this experiment, I will explain my web-based tool called Uniform PCM Quantizer. This simulator is designed to visualize the complete process of code modulation, uniform quantization used in pulse code modulation, or PCM, and to show how changing the number of quantization bits affects signal quality. The website is interactive, so whenever I change the bit depth or the signal frequency, all the graphs and performance values update automatically. Like like this, if I change these parameters, then the graphs will also change accordingly. At the top, we have two input sliders and three output parameters. Okay, so the first slider is quantization bits. Here this is the quantization bit, and this controls the number of bits used to represent each sample. Increasing the number of bits used to represent each sample. Increase the number of quantization levels, which produces a more accurate digital representation of the analog signal. The second slider is frequency. This changes the frequency of the input sine wave. It allows us to observe quantization on signals which with different rates of variation, while the quantization process itself remains the same. On the right slide, the simulator displays three important performance matrices. The first is MSE, or mean square error. This measures the average error between the original and analog signal and the quantized signal. A smaller MSE means the quantized signal is closer to the original. The second value is actual SQNR, which stands for signal to quantization noise ratio. This is calculated directly from the simulated signal and tells us how much stronger the useful signal is compared to the quantization noise. The third value is theoretical SQNR. This is the ideal value predicted by PCM theory. Comparing the actual and theoretical values helps us validate that the simulator behaves accordingly to the expected mathematical model. Now I'll explain the main graph. This graph compares two signals. The gray smooth curve is the original analog sine wave, and the blue staircase waveform is the quantized signal. This staircase shape is the most important feature of the uniform quantization. Instead of changing continuously, the signal can only take specific discrete amplitude levels. Every analog sample is rounded to the nearest available level, creating these horizontal steps. With 3 bits, the signal has only 8 quantization levels, so the staircase is quite noticeable and the difference from the original waveform is clearly visible. As I increase the quantization bits from 3, 4, 5, 6, like 3, 4, 5, 6 or 7 bits, watch how the staircase becomes much finer. Uh, the steps become smaller and the blue waveform begins to overlap the original gray signal much more closely. This visually demonstrates the increasing the bit depth, reduced quantization error, and improved signal quality. If I change the frequency slider, the waveform oscillates slower, faster and slower. The amplitude remains the same, but the number of cycles changes across the graph. The quantization process still creates staircase levels, showing the quantization depends on amplitude resolution rather than signal frequency. Understanding the performance values. Now let's observe the numerical values while changing the bit depth. At 3 bits the MAC is relatively high and the actual skewness is around 19 dB. If I increase the bit depth to 5 bits, the MAC decreases significantly while the skewness increases to above 31 dB. This tells us that every additional bit improves the signal quality while reducing quantization noise. One important observation is that the actual skewness is always slightly lower than the theoretical skewness. This is expected because the theoretical values assumes an ideal quantizer while the simulation includes practical numerical approximations. Thank you. Now I'll briefly explain the working of the simulator. First, the website generates a continuous signal sine wave at the original analog signal. Next, based on the second select number of bits, it calculates the variable quantization level. Every sample of the analog signal is then mapped to its nearest quantization level, producing the staircase waveform. After quantization, the simulator calculates the error between the original and quantized signals. From this error, it computes the mean square error and actual skewness. Finally, it compares these values with the theoretical skewness and generates the complete analysis table for bit depth from 2 to 8 bits. All of this calculation happen instantly whenever the user changes either slider. Thank you.